Thank you very much for the introduction, and I thank the organizer for the invitation. So I'm so glad to be back to Vienna. And so so the bounded image theorem is something claimed by William Thurston in his proof of the uniformization theorem. And but nobody knew the proof because he didn't publish the proof. And so last year, with Cyril Lecuire, actually the chronologically this comes first, then with Cyril Lecuire, so we succeeded in proving this bounded image theorem, and using the rather modern technique of the Kleinian group theory. But so we used the tools which didn't exist at the time of the Thurston. So after proving this theorem, I started to consider think about what was the real proof, the original proof that Thurston had in mind. And now I already come to I've almost come to the conclusion of so I could now imagine what Thurston had in mind. So I wrote some paper on this topic. So this is already in an archive, and this is to appear in Geometry and Topology. And for this, so I wrote a paper or chapter. So in the tradition of the Thurston. So that's a series of books I edit with another. And in a volume 3, so the paper on the chapter on this topic will appear. So this is a kind of a reconstruction of Thurston's original argument for the bounded image theorem. So, but in this talk, I would rather focus on the first part rather than the second part, was real proof. So I focus on what Thurston had in mind to prove this theorem. So before starting, so maybe it should be better to say something about uniformization theorem before really stating the bounded image theorem. It's better to explain the motivation of that theorem and also the background of this theorem. So it is a part of the Thurston's uniformization theorem. Or for Haken manifold. So it appeared in the 1980s, I guess, or from the kind of the announcement already appeared in the 1979 or something, but the real argument appeared in the 1980s. And so Thurston wrote a paper whose title is Hyperbolic Structures on 3 manifolds. So his plan, the original plan, was to publish a series of papers consisting of the 7 parts. And it should have given the entire proof of this theorem. But what exists is just the 3 of them, 1, 2, 3. So one is published in the Annals of Mathematics, and the 2 and the 3 exist in the form of the preprint in the archive. Now you have a kind of the published version in the collected works of the Thurston, but the paper didn't appear in the ordinary journal, the 2 and 3. But so the one was really published. Okay, so let me just state the uniformization theorem. So the M is the assumption is the M is a Haken manifold. So Haken manifold is a compact 3 manifold which is irreducible. Irreducible means every embedded sphere should bound a free ball. So it is irreducible. And the other assumption is contains an incompressible surface. So that's the definition of the Haken manifold. So first, the uniformization theorem for Haken manifold says that if the free manifold Haken manifold, if M is an toroidal, I will explain what that toroidal means. A toroidal Haken manifold. Well, the assumption in boundary M is either empty or consists of tori. Then the conclusion, the interior of M admits complete hyperbolic structure. Hyperbolic structure. So its first theorem, stating that the hyperbolic structure really exists quite in a generic form in a free manifold. So that of course that's before the Perelman proof of the geometrization theorem. The geometrization theorem was just a conjecture at that time, and this is a kind of justification of the conjecture. So for something called the Haken manifold, the conjecture was true. That's what he claimed. Okay, so that's the uniformization. So let me show you what the toroidal means. So the manifold M is said to be toroidal if any pi1 injective map from a torus is homotopy into boundary. So especially if boundary is empty, this means that there's no pi1 injective means that it induces injection between the fundamental groups. So in particular, if M is closed, then this means that there's no pi1 injective map from a torus. That's the meaning of toroidal, being toroidal. Okay. And now, so let me show you what was the strategy to prove this. So in the 7 papers, so Thurston tried to show that, prove that, and the strategy, basic strategy is something like that. So if M is a Haken, then there's something called a hierarchy. So this naming is due to Walthausen, but the basic idea already appeared in the Haken's paper. So what the hierarchy is? So if M is Haken, so it contains some incompressible surface by definition. And then we can cut M along F. So so you have some. Well, the typical case is when M is closed. So then you have some incompressible surface like that, and you cut M along this. So so you have 2 copies of F, probably F1, F2. That's the copies of this F. So you get such a kind of disconnected manifold. Well, if it's separating, this is disconnected. If it's non-separating, it's connected. Anyway, so you have such a kind of. Again, this is a Haken. Well, it's easy to show that. So then you can cut this by the second surface. Well, it's not good to put this. So this should be F1 or something like that. Then you cut again and continue the process. Now, what Haken showed that actually this process should terminate in a finite steps. After the finite step, what you get is just the union of three balls. So this is something called a hierarchy. So if you have a Haken manifold, then there is a system of this kind of the sequence of cutting the manifold along the surface, and after finite steps, you get the union of three balls. Okay. And so because we are assuming the M is Haken, so for this M, we have such kind of hierarchy. So the strategy of the proof of the uniformization theorem is just the induction on the hierarchy. Except for the case when M is a surface bundle over S1. In the case when M is a surface bundle over S1, there is a different kind of argument which shows that. So that's the case when the mononormy is a pursuit anorthof. And for that, there's another theorem. Actually, that in a part 2, Thurston actually gave a proof for the case of when M is a surface bundle. So except for this case, so you have a sequence of the hierarchies, and the proof is based on induction on this hierarchy. Oh, I should. This. And actually, the argument for each step is quite similar. And what is most important is the last step. So so you have M, and you have a incompressible surface embedded in M. And you have, if you cut M along F, then you have such a thing. So that this should be M. This is M. This should be M1. And now I should in such a way that F1, F2 as copies of F. And in the last step, so what was the last step of the induction? So the assumption of the induction is M1 has a hyperbolic structure, but something called a convex, compact. But here I'm assuming that M is closed. We can argue in the same way when M has a torus boundary, but it just complicates the description there. So I'd like to stick to the case when the M is closed. So then M1, so the assumption of the induction is that M has a convex compact hyperbolic structure. So what we should prove that under this assumption, so that this should be proved. M also has a hyperbolic structure. So this is something pasting hyperbolic metric along the surface. So actually, there's a tool for that. That's called the Maske's combination theorem. So the point is to deform the convex compact hyperbolic structures on M1 so that the Maske's combination can be applied. So that's what Thurston thought about. Yep. No, not at all. So this is something called the quasi-Fuchsian. In general, it's impossible to make it totally geodesic. So it's a quasi-Fuchsian, and by pasting that means the quasi-Fuchsian corresponding to that and corresponding to that can be identified by an orientation reversing way. That's what we'd like to do. So to state it more precisely, so we need a notion of the skinning map. So suppose M1 has a convex, compact hyperbolic structure. Then there's a theorem by Marden, or probably R4 pairs, and Kramashkit. This is a special case, and the general statement is by Marden, saying that there is a so this is because this is incompressible. This is an incompressible boundary. Then there is a parameterization of the space of the convex compact hyperbolic structures on M. So let CCM be the space of the convex compact hyperbolic structures on M. Modulo isotropy. Then what Marden showed is that there is a parameterization of this structure by the Teichmüller space of the boundary. But in our case, so suppose this is the picture, then in our case, this is just the product of the two Teichmüller spaces. Teichmüller spaces of F1 and the Teichmüller space of F2. Okay, there's a parameterization like that. Okay. Now, it come here. So now we have a parameterization for the convex hyperbolic structure on M1, but we'd like to take a covering associated with the pi 1 over F1 or pi 1 over F2. So there is a map from the CC of M to the Teichmüller space. So from CC of M, take a covering, or the two coverings actually, two coverings associated with F1 and F2. Because we are considering the convex compact hyperbolic metric on M1, after taking covering, it's again convex compact. That means this is, if you take a covering, this corresponds to a quasi-Fuchsian structure, the quasi-Fuchsian group. So, and by R-force Baer theory, we know that the quasi-Fuchsian space is parameterized by copies of two copies of the Teichmüller space. So you have a parameterization. So for F1, you have a parameterization, something like F1 times F1 bar. So I put bar because so by natural orientation of on the boundary. The structure is something obtained by the orientation reversing marking. And for F2, you have also something like that. So composing this map and that, probably this should be called something. I put Q for it. And this should be something like, this part should be P1, this should be P2. So if you compose P1, P2 to Q, so we get the map from TF1 times TF2 to TF1 times TF1 bar times TF2 times TF2 bar. So this means, so if you have fix some conformal structure at infinity for F1 and F2, so automatically there's some conformal structure hidden here. And after taking covering, this hidden structure appears, and this gives the second factor here. And so for something like Mn, so this is again M. And the third factor is again N. So the new coordinate on the second and the fourth. So I should write it like sigma 1 M, N, probably, and the sigma 2 Mn. Okay. So in this case, actually, in this case, that the F2 doesn't, the N doesn't contribute to here. But anyway, so it's just a function of M and N in general. So then taking Mn to the sigma Mn, sigma to Mn. So this is a map from TF1 times TF2 to TF1 bar times TF2 bar. Now, to get M from M1, you have to paste them up. So there is a kind of the identification of two boundaries, which gives F. Okay. This identification is denoted by iota, and I regard it as an involution. So F1, the iota sends F1 to F2, and sends F2 to F1 in an orientation reversing way. So this is orientation reversing involution. So after that, so we have a sigma, and then you can just take F2 to here and F1 to there. So by the involution, then you get now map from TF1 times TF2 to TF1 times TF2. So this is the composition of this map and the involution. So this map is called the skinning map, or this map anyway. So the called the skinning map. Probably this sigma is called the skinning map. Anyway, so this is sigma. Okay. And now I can state the bounded image theorem. So probably it's better to change the backboard. Okay. Let me say one more thing. So the mask-kit combination can be applied if there exists a point in a product of the Teichmüller space such that the skinny maps, this fixes that point. That should be written like that. So if there is, if you can find M and N, which is fixed by the skinny map, then you can paste the structure to get the hyperbolic structure on M. That's the consequence of the Maskit's combination theorem. Okay, now I can state the bounded image theorem. So to prove that, if we can prove that, then we can prove the last step of the induction. But to prove that, the Thurston showed the two theorems actually. The one is something called the bounded image theorem, and the second is something called the fixed point theorem. So the fixed point theorem is a kind of the theorem directly gives this point, but it depends on the first theorem, the bounded image theorem. So he first showed the bounded image theorem, and using that, he showed that fixed point theorem. So here's the statement of the bounded image theorem. So the situation is like that. And then there exists a constant and zero depending and not depending on the topological type of M1, such that the image of the skinny map, so this, iterated by n times, so the n is greater than, such that for any n greater than or equal to n naught, the iteration of the skinny map, the n times iteration, the image is precompact. So its closure is compact. Teichmüller space is the product of Teichmüller space is just homomorphic to the Euclidean space of some dimension. And inside that Euclidean space, this is a precompact. That means if you take the closure, that's compact. So that's the statement of the bounded image theorem. And actually, so Thurston didn't give a proof for this bounded image theorem. And as I said at the beginning, so we with Cyril Lecuire, we have a proof, but actually, so we used many things which didn't exist at the time of the Thurston. So what I'd like to show here is how Thurston tried to prove this. And so I could reconstruct his proof just reading the materials which appeared in his collected works, plus some lecture notes or so. Actually, in the first part of the paper, series of the paper, so Thurston gave a kind of that flow chart for the proof. And if you, so it's very, so it's just one page flow chart, but if you just copy it and magnify it by 3 times or something, then I can just follow what he intended to do. And actually, I found out that this theorem was proved another theorem using another theorem, which is called the broken windows only theorem. which is contained in the part 3 of the series. So the part 3 exists as a prepared form, and so you can see you can just see the theorem in a. Actually, this is a kind of main theorem of the part 3. So let me state what the broken windows only theorem. So situation is quite similar. So M is so here M is something like M1 there. So M is an atoloidal. Probably it's better to stick to the symbol M1 because what that corresponds to is just the M1 there. So atoloidal Haken manifold. With boundary, and the boundary is incompressible. And we are considering a case when M1 has a convex compact hyperbolic structure. And so by AH of M1, we considered all complete hyperbolic structure on M1 modulo isotropy. So this is the same as the space of the faithful discrete representations of the pi 1 of the M1 into PSL to C modulo conjugacy. Just taking the holonomy of this structure, then you get the faithful discrete representation. Okay, now to state the theorem, I need some definitions and which are used in the three-dimensional topology, what's called the characteristic submanifold. So we are now considering compact three-manifold, which is irreducible and with non-empty boundary, which is incompressible. Then we can apply the theorem called the Jacob-Scharen-Johansson theorem. So there's something called a characteristic submanifold. So this is what the Jacob-Scharen-Johansson theory implies. So in M1, M1 was the right symbol. So in M1, the collection of submanifold V1 up to Vk, which are disjoint. And each Vj is either an I bundle such that Vj intersection boundary of M is an associated boundary I bundle. So here we should draw a picture. So we have a M1, something like that. So the part of that, there is something like an I bundle. So this is a part of this is one example of it. So it's an I bundle such that if you consider the intersection with the boundary, they correspond to the associated bundle boundary I bundle. So that if you consider the 0 section and 1 section, then that should lie on the boundary. So that's one example of the characteristic submanifold. The other example is a solid torus, such that the intersection with the boundary is parallel. Okay, maybe it's a disjoint union of incompressible annuli and which are parallel on boundary of Bj, but they are not parallel in the three manifold. It's something like this. So you have a solid torus here. So you should consider case like something like that. This is the meridian of the solid torus, and you have something like that, and the intersection with the boundary is annulus, union of annulus. So there are two cases like that. So then, and the union of like that, and they are characteristic in the sense that it's a unique up to isotropy, and it has a property that any properly embedded annulus in M1 can be absorbed. So that means can be properly isotopic into one of E1, EK. And so such a thing is called a characteristic submanifold. Well, actually, we impose some other condition that this should be minimal among the submanifold with this property. But anyway, there is something called a characteristic submanifold of M1, and it consists of the I bundle and the solid tori. And now I can state broken windows on this theorem. So this is broken windows on this theorem. So the theorem consists of the two statements. The first statement is something like that. So that if you consider the something, so we deform this characteristic manifold to something else. So that when Vj is I bundle, then we define Wj is equal to Vj. But if it is a solid torus, then we deform it, we change it to its frontier. So the frontier is just something like this. It's a boundary as a subspace. So these are frontier. Okay, and we consider the union of all Wj. Then the first statement is that if you restrict AHM to this subspace or submanifold, that is the complement of W, actually, M1 minus W. So if you, so for each hyperbolic structure, we consider the restriction of the hyperbolic structure on this subspace, submanifold, then this is compact. So although this AH of M may not be compact, if you just consider the part of the manifold, which is the complement of W, then it is compact. That means if the non-compactness of the AH of M appears, that happens only in W. So that's why it's called a broken window theory. So that if the structure breaks, that happens only in W. W is a window. So that's the first statement. And the second statement is like this. So there exists W prime in W. So that's, so when Wj is the I bundle, so this is a sub-I bundle. So you restrict the base space to some incompressible subsurface, that's a sub-I bundle, or just pick up some component of the frontier. So you forget some of them and you just pick up some of them. Then that's a W prime. So the W prime is a kind of subfamily of W. And there exists such a thing. And for any given sequence Mi in AH of M, so the W prime depends on this given sequence, exists the W prime and the subsequence Mij of Mi such that so for any G in a pi1 of M1 such that the restriction of Mi to G converges, diverges. It should be, which is better to, it's easier to describe. Probably it's easier to, it's easier to say that it converges. Mij, restricted G converges if and only if the G is conjugate into I1 of C, where the C is a component which is a component of the complement of the W prime. So that means, so if you have a, well, let me draw a figure somewhere. So you have a manifold M1, and probably there's something like W prime. So it's a kind of subset of W, and if for given sequence, if that converges, then that should contain, that should be induced from the pi1 of this complement of this. So if there's something, well, coming from W prime, then that should diverge. Something like that. So it's a second statement. So, so the first one is something should be called a broken windows only. And the second one should be called you can find a diverging locus. So if the divergence happens, then you can find the cause of the divergence. And the cause of the divergence should lie in a subset W prime. So if it diverges, that should contain some element in a W prime. So if it lies outside W prime, that should converge. That's the meaning of the second statement. So that you can realize the diverging locus geometrically. That's the statement of the second one. And what's surprising is that this second statement is actually false. So there is a counterexample. So we can construct a counterexample concretely. So you consider something like that. So you consider something called the book over I bundle. So you consider 4 I bundle. So you consider sigma 1, sigma 2, sigma 3, sigma 4, all of which are surfaces with one boundary component. And we paste them to a solid torus here along an annulus. And well, it's easy to see this has a convex, compact hyperbolic structure. And you can consider the AH of M. Okay, so the AH M1, well, so M1 should be this. And now we consider, so we fix some element in AH or M1 or anything, or probably convex compact structure, convex compact hyperbolic structure. Then you consider the then twist along here and there. So this is attached to solid torus along an annulus. So we consider then twist along an annulus here and the annulus here. So you have 4 annuli actually. You pick up 2, the first and the third, and you consider the then twist along A1 and then twist along A3, and compose them and iterate. Something like that. Okay. And then we try to find the W prime stated in the Thurston theorem. But we can show that it doesn't exist actually. So why? Because if you restrict the structure to this subset, sigma 1 plus the solid torus and sigma 3, that converges. Because sorry, this should be. Well, it's better to write it this way. So I wrote it with some orientation, but maybe it's better to understand. It's easier to understand if we put it that way. So that means, so you consider then twist to that direction, and then twist to that direction, this one, that, and then if you compose that, they cancel out. Because this is a right-hand then twist, and this is a left-hand then twist. So they cancel out if you just consider the union of these two. So this is cancel out for this set. The first is right, and the second is left. Well, if you write that way, that these two are those of them are right. They commute, they are disjoint. So let's cancel out. So for this one, it should converge. So that means W prime should be disjoint from this part by the definition of W prime. On the other hand, so if you consider something like that, well, it's disjoint from these annuli, so it also converges. So this converges, and that also converges. But if you consider the union of sigma 1 plus sigma 2 like that, that diverges because there's only one then twist here. Okay? So converge, diverge, and this also diverge. So then you can find a W prime anywhere. So this is a counterexample actually. So actually the second statement is false. But the Thurston proof of the bounded image theorem relies on this second statement, actually, surprisingly. So I don't have any time. So just say this. So the second statement of broken windows only theorem implies bounded image theorem. So as I don't have enough time, so let me just say it without writing it on the board. So so suppose that so it's by contradiction. If the bounded image theorem falls, then you can find a sequence such that for any n, so you can find a sequence mi such that for any n, this diverges. This diverges. Okay? Right. So, but this is in the Teichmüller space. So instead of Teichmüller space, we consider the space CC of M1, no, sorry, the AH of M1. So we divide the argument into two cases. One case is it converges in the AH of M1. So for that, there's an argument involving the tameness and the covering theorem, and we can show that actually it's a contradiction. So the difficult situation is when this also diverges in AH of M1. And in that case, we use the broken windows only theorem, especially this part 2. And we can show that there is something called the W prime, and it gives an annulus in M1. So it gives an annulus in M1, annulus in M1, which comes from the boundary frontier of the W prime. And we have something called well, it would be better to use the other. So we have a M1 like that, and we have an involution facing that. And we can show that if it's a diverging locus, a part of the W prime, then iota preserves this. So this, if you map that, then there's another annulus one of whose boundary is pasted there. Then we repeat the process. So because for any n we have that, so we repeat the process. So we have a family of annulus which can be extended by n times in M. And by usual argument of the Haken or Walterhausen, you can see that after n steps, that should stop, forming an incompressible torus in M, which is a contradiction because M is a toroidal. So that kind of argument works if we admit this second part of the theorem. But this second part is false, so I cannot reconstruct Thurston proof by this. But I just try to understand what Thurston had in mind, and that's all. Thank you very much. So that I should stop here.